Good morning, everyone. It is 7 a.m. and this is part 5 of 10 in a 10-part webinar series called Learning Math in Context. I am super excited to be here. I am Sara Werf. I am the MDE Academic Standards Math Specialist, and I am excited to be with you. But for the first time ever in this 10-part series, I have a guest, and I'll let her introduce herself.
Good morning, everybody. I am still at Minnesota Department of Ed. I used to be the STEM and computer science integration specialist. I now support federal title programs specific to Title II, which is about professional development. Thanks for having me, Sara.
So you'll hear from Sara in a little bit. As I've said, all the things that we're sharing with you today, you can find in the links to this webinar series. I have almost everything in there already, so you can go and check it out. If you're watching the recording of this, you can find the links in the description below. This is part of our webinar series that's connected to the 2022 Minnesota Math Standards that will be fully implemented in the 27-28 school year. And we're looking at our second of 5 dimensions, computer science. So you'll hear us talk about that today. If you went to the standards and read about it, there's a small paragraph about computer science and the other contexts in there. And today we hope to flesh that out. So 2 weeks ago, we talked about what it means to use real world context in math. We're going to talk about computer science today, and then we'll move on to the other ones in December and January. So computer science context, it's an independent field of study that focuses on learning how to think computationally and adapting and creating new technology. It's early in the morning, but I'm going to have you think about that word computationally and listen for it in our upcoming slides as we're moving. These are all us talking about learning math in context. And so the definition we're using for context in math refers to situating mathematical ideas, our benchmarks, our standards, in everyday real world. And I added for this webinar the phrase computer science situations. So we're going to take math and put it with computer science situations. And if you're like me and you haven't done that enough in your career, we're going to try and give you some good ideas to answer this question. These are the 3 questions that we use in planning for the new standards, because we want an equal amount of energy spent on 3 things: conceptual understanding, procedural fluency, and application, which is our context. So we're going to answer the question, what authentic opportunities exist for the application of the standard or benchmark we're thinking about to real world problems? And in this webinar, computer science. So let's take a look at the very first benchmark in kindergarten. In our standards, you will notice at the end of that benchmark, notice and describe patterns in data-rich situations. You will find a pound symbol, a number symbol if you're old like me, or a hashtag if you've been around just in the last 10 or 20 years. And that hashtag means it's computer science context. I'm going to have Sara tell you a little bit more what we mean by computer science context.
We wanted just to start real quickly if you're interested in diving into what Minnesota is doing with computer science. So we do not have standalone computer science standards in this state. A couple of years ago, a group of leaders from around the state came together to develop a state strategic plan to think about how to increase access to computer science across the state. And that's a good resource if you're interested in diving in more on what is recommended. But let's dive into the definition of computer science. So you see a lot of different symbols on this slide. These symbols all kind of put together, talk a little bit about computer science and the next few slides. So as I'm starting here, think about to yourself, what do you think computer science is?
Feel free to
And
put
we're going to,
something in the chat. You don't have to, but feel free to put in the chat.
thanks. And we're going to start out with what computer science is not. So as you're thinking about and putting in the chat your definition of computer science, let's eliminate some things. So some of the things computer science is not using educational technology, is not teaching students how to use Microsoft Word or PowerPoint or even Google Slides. It's not keyboarding. It's not information literacy, and it's not playing computer games. Now,
What?
I'm also a librarian, and so I think all of those things are really important, but they're not computer science. A couple of other misconceptions we have about computer science out there is it's not only for students who want a career in computer science. It is not only for those students who are excelling in math. So often we say, oh, you're already on Algebra 2, go take a computer science class. It is not only for those students who excel in math. It is not done in isolation. In fact, when we look at how computer science is done in the real world, it is often done on teams, and those teams are needed to ensure the work is continuing well. It is not only about computer programming, and you'll see some examples as we're going through today. And finally, it's not just for older students. We're seeing students doing computer science, whether with devices or without devices, in an unplugged manner, as we call that, as early as preschool, to start thinking about those habits and those ways of thinking. So here's a lot of things computer science is not. Anybody have any thoughts about what they think computer science is? Didn't see anything in the chat, but that's okay. We'll just keep thinking about what is computer science.
Ooh, Christine said problem solving.
Oh yeah, for sure, Christine. Super so much problem solving. So this on the screen is our very complex definition of computer science. This is a definition from the K-12 CS framework, but it is also the definition that is in Minnesota state law. Now we're going to break it down a little bit and look at some of those words in there that have really kind of jargony meanings. So we're going to start with algorithmic processes, and the little diagram on the left, I see Penny putting algorithms in the chat. Absolutely. And algorithms are just a set of steps that help you reach a goal or solve a problem. And that's all an algorithmic process is, a set of steps. The next kind of concept in the definition that I like to break down is hardware and software. And it's just like it sounds. The hardware is the hard stuff, the computer, the mouse, the screen, the hard drive inside, and the software is the stuff you can't touch. It's the programming that makes all of the hardware work. And so we always talk about hardware and software with computers. And finally, we do talk about the impact on society. It's not just about creating things with computers, but it's also thinking about how those things that we create with computers and technology affects the world and how we can use it to solve problems. So that is a very large definition of computer science. And in Minnesota, we are thinking about how to integrate computer science into all content areas. And as we think about integrating computer science, we know that not all students and teachers are ready to go full on with doing programming in all their courses. And so we have developed this, what's the word for this, Sarah? Progression. There we go.
Yeah.
Integration progression document to help you think about what might it look like if I'm just starting to think about how to integrate computer science. So at the beginning levels, this is where you're going to start. You're going to start by exploring computational thinking concepts. And Sarah has some really great examples we're going to talk about in a little bit for thinking about what this looks like in math when you're just exploring computational thinking. You'll notice this word that's being circled, computational thinking, it's going to come up a few more times. So then once we're starting to feel more comfortable, we might start applying. So we might use some simple modeling or some introductory coding tools. Again, we're going to apply computational thinking concepts. And then if we're feeling a little more comfortable, we might start analyzing and debugging. So we might be trying to solve some complex problems. Again, we're going to use computational thinking to break down those problems and look for patterns. And then finally, the last two, we're going to start really actually programming independently, designing our own programs to help solve and address real world problems.
So, what do you notice? I'd love a few people to throw things in the chat right now. And what do you wonder? Because we've been using this phrase computational thinking. And I think in order to embed computer science into mathematics, we really need to have a depth of understanding of computational thinking. And the good news is the computer science people here at MDE put together a one-pager about what that is. And these are some of the icons that they used when they were describing what it was. And I'm wondering if this gives you any clues. Tell me some things that you notice or describe. throw in some words or phrases that you think about. Oh, yeah, there is some crossover with the science practices. In fact, these represent the computer science computational thinking practices. And so, this idea of math practices in my webinar series last year, science practices if you've been fully implementing the science standards, and more. And it kind of looks like a checklist. Somebody said coding if then statements is another thing. I see the word process there. Oh, there's also a notice of connections to social studies. By the way, I'm pretty sure my social studies peers are going to join me at the next webinar. So get excited because our content areas do have a lot of connections. Well, these icons are represent the practices of computational thinking, which is really just a set of ideas and thinking skills that help you solve problems in a way that both people and computers will understand. I think in math, we've done a good job of working with students to solve problems in a way that people can understand, but can we simultaneously do that so that computers could also understand? And so there are 6 practices. And when I saw these practices, I was like, this feels like a math class. Like I think of math as studying patterns. And so that's one of their practices. And in fact, patterns is a big deal as part of the science standards as well. So computational thinking has, each of these things has a definition, and you have access to all these slides. And we're going to give you a link to the one pager where all of this comes from. But I think and then the other thing I would say is that computational thinking not only has these 6 practices, but it has these 5 ways of engaging in developing those practices. And so these words, I love the word tinkering. It's a word I've started to adopt in my own work. I love asking students to consider tinkering as well as some of these other things. So Sarah, is there anything that I missed related to these?
Nope, not at all.
So I've spoke about one pager and I have it linked in all the things that we've shared with you. I highly recommend, you can also find it at the MDE computer science page if you Google MDE and computer science. But computational thinking is these 6 practices and these 5 ways of doing it. And one of the best ways you could just start exploring and dipping your toes in it is to start using the vocabulary of computer science in your classroom with students, in your planning with other educators, and think about how do I give my students opportunities to tinker, to persevere, to debug, to create, to collaborate. I heard Sara said when she was talking about the myths that being in computer science is not done in isolation. And you're often working in teams and collaborating. So I want to give you an example of one of these practices, decomposition. Me and some of my peers in science and English language art, we did a webinar on these computational thinking practices. You can find that linked below about a year ago. And I talked about decomposition, and I did a lot more. I had 15 minutes. I'm just going to give you 2 minutes of what decomposition in math might look like. Decomposition in computer science is breaking down a problem or a system into smaller parts and components. And in math, we use that term all the time. We break things down. I'll give you some examples. Here's a student that's adding 2 numbers, and in order to make sense of it, they've decomposed that 38 into 13 and 25, because then the 87 and the 13 can be recomposed and put together to make 100, making it a little bit easier for them to do it. A student might decompose when they're thinking conceptually using arrays about their math facts, and they might not know 6 times 7, but they might be able to split that 6 rows apart and have 2 sets of 3 and make that easy. When they're splitting things apart and chunking them, they're decomposing. Or maybe they're taking a fraction and turning it into a mixed fraction, and so they want to pull out a whole and the rest of the fraction and make a mixed fraction. That's decomposition. Even when you get into high school and you're factoring trinomials, you might look at a term and say, wow, it would be easy to factor if I could decompose that middle term, and then I could factor out a common factor and do things like this. If you look at our new standards, you will find the word decompose, compose, or it talks about strategies. using decomposition. That word in computer science is also in our standards. And it's not just for number and algebra, it's all over the geometry standards. In order to make sense of the formulas for the area of a rectangle and the area of a parallelogram, we can decompose a parallelogram into a triangle, another shape, shift them around and recompose them. And that allows students to build connections between mathematical ideas, supporting them and conceptually understanding why that works. So why is decomposing in math helps? You can go back. I have so many hidden slides on decomposition and other ideas in math, but there's a lot of things that it does, and you can pause and read this slide if you want. It builds connections between different geometric concepts. It builds flexibility about numbers and operations and shapes, and it prepares students for higher level math, and it starts to prepare them for computer science.
And when we do decomposition in computer science, we're often doing it because it's going to help us. It's always about helping us solve a problem, right? So it's going to maybe sometimes help us design an algorithm that might help solve the problem. Once we've broken it down into its parts, we can attack each part separately and design an algorithm to help solve the smaller problems. The smaller parts become more manageable when we're looking at a large problem, or it's not always a problem. Sometimes it's something else, but the smaller parts are always easier for us to understand. We also really often are weaving decomposition together with pattern recognition and abstraction. So often when we decompose something, we start to see the patterns. It makes the patterns a little bit more obvious when we're looking at the smaller parts. And then that decomposition might also allow us to kind of abstract the details and look for generalizations. And again, that can help us kind of illuminate patterns and create algorithms that might help us solve the problem or design something. So a lot of similarities with decomposition in math, really about breaking it down to make it easier to understand or to solve problems on that smaller scale.
Sara put this slide together, and when I read this slide and some other ones coming up, I was like, wow, this is just the definition of math, the study of patterns and relationships, and then using those to build generalizations in mathematics, because that's math. Math is not just arithmetic. I asked Christopher Danielson in the webinar that I spoke about to talk to me about decomposition in mathematics, and he said it relies on noticing various kinds of structure. For example, the transition from arithmetic, hey, these odd numbers, to algebra, all the odd numbers, requires an understanding of structures, not just familiarity with certain facts. And if you're like, what was he talking about odd numbers? Go check out the webinar and you can see where that came from. But structure is something super important to understand so that we know how to take it apart and put it back together when we recompose it. All of this builds on not just doing math in real world, but the legs of this rigor stool are all connected. It supports students in building conceptual understanding. So I want to build some connections here for you. We've been talking about computer science and practices. That one pager on computational thinking, those are the 6 practices of computer science. And in math, in our new standards, there are 8 practices. So there's a relationship between those practices. In a minute, Sara's going to talk to you about the concepts, the standards of computer science that we use to build our standards. And those are going to be connected to the actual 2022 math standards. That's the concepts of mathematics. And the goal here is to connect all these things. So the practices we've started to allude to already are things that already have a connection. But now we're going to spend a little time talking about the concepts and how they connect.
So the Math Standards Committee worked by looking at the Computer Science Teachers Association standards. These are the 2017 standards. They're actually in the process of revising them, and the new CSTA national standards will come out, should come out in the summer of 2026. And so when you look at the standards, this is a really great one pager that talks about all of the standards and the various concepts that Sara was talking about and the connections we really saw to math as the committee was looking through. And they were really looking for connections between math and computer science. They weren't just adding computer science in for computer science sake. They were looking for those overlaps, those authentic opportunities for context. And so one of the concepts that really sees connections to computer science, not surprising, is the data and analysis concept. And the other one where the committee found some connections was the algorithms and programming concept. So when you're looking at the Minnesota benchmarks, in addition to all those places that you can see overlap with computational thinking, you can also see overlap with these computer science concepts. Go ahead, Sara. And one of the resources that we created for you to think about that will be coming out soon is this learning progression that specifically looks at only those benchmarks that have been identified as being connected to computer science and looks at their connections to the concepts and the benchmarks. So the CSTA standards have both these concepts and benchmarks. And again, in particular, we're looking at the data and analysis concept, which has these two sub-concepts of inferences and models and collection, visualization, and transformation, and then the algorithms and programming concept, which breaks down into modularity, variability, and control. There are great definitions available for you in this learning progression document that you can reference as you're thinking about what do all these words mean? And it's broken down by grade level, so you can see as you go across the grades how the different math benchmarks are building on each other to also build that kind of computer science understanding as well. So this is a resource that it will be coming out soon on the math page and maybe the computer science page.
Math implementation page, yeah.
Yes.
So you'll see a lot more. And by the way, I have a bunch of hidden slides with all the definitions of that. We just didn't want to read all those definitions in a half-hour webinar to you. So feel free to look at the slides and check those out. You might be thinking, what did the standards writing committee, what did they do? Well, they selected some benchmarks, and you can see how many benchmarks per grade. And they connected the math benchmarks to the CSTA benchmarks. And you're like, well, how do I know what they connected it to? I have some good news for you. And I'm going to do it through showing you two different examples of two different benchmarks. So remember that first kindergarten benchmark where you see that hashtag saying, hey, you could teach this math benchmark and connect it to computer science. I'm going to give you an idea of what that might look like. And so we're going to start in kindergarten. And if you were at my last webinar, you saw these cute little kindergartners, and I talked about an example with them. But this time in this picture, I want you to notice that there's a sun back there, because that will come back to show us something that we could do. I want to give a big thank you to 3 of the committee members that worked with Sara Carter to do this work. In fact, they've been doing some professional development at our state conferences. Mark Nicknicky, Jillian Tomsky, and Indriani Lamarie. They are all classroom teachers who are thinking about what does this look like at elementary, middle school, and high school. We had some of the most fabulous Minnesota teachers who are helping with this work, and they put together a resource that I'm going to show you right now for every single one of the benchmarks, and you're going to have access to it right now. The only way you'd have access to it now is if you were in Duluth last year and went to their session. And so for every single math benchmark, if you look on the left, you'll notice there's that first kindergarten benchmark, and underneath it is the CSTA benchmark. And so let's look at that progression of how you start to implement computer science. And we always recommend just start with exploring. Have your students explore this idea. You don't have to jump all in. Maybe it's thinking about the common vocabulary that exists between the math and the computer science benchmark. And so I was looking at this and I'm like, dude, it's always important to talk about patterns in math. So that's one of those practices from computational thinking I'm going to do. And I'm going to have our kindergartners tinker. I'm going to do something in class where they have a chance to tinker with something and collaborate with their peers on something. So I looked at this and said, hey, build a sorting activity. I was like, hey, were you at my last webinar where we did a sorting activity using buttons? Because I could teach that real world activity and use a counting collection and do some sorting and say to students, give them a collection of something, in this case it's buttons, and have them start tinkering with it. And as students, they start sorting them in a way that makes sense to them. It looks like they put the weird cupcake button in one of the things all by themselves, but it kind of looks like they are sorting these by color. And you might say to students, your kindergarten students, as they were collaborating, tell me what you were doing. And they'll start to talk about the patterns they're noticing. Maybe other students are sorting it by size, but you're giving students those a chance to engage in those practices that will build computer science thinking in more and more sophisticated ways as they go through the K-12 system. If we look at that kindergarten benchmark again, I could think about pattern recognition, but I might look at the other possible curricular connection. And we have this for every single benchmark. So don't say you don't have resources of how to implement computer science. I might want to link observations of daily routines like the weather. Remember that sun in the picture of the kindergartners? In recognizing patterns and data. So maybe you're thinking not only we're going to do work on the practice of pattern recognition, but we're also going to think about data collection in kindergarten. And so I'm going to give you an idea of what that might look like. So maybe every day when students come to class for 1 month, you are noting, what is the weather outside looking like? I'm looking outside my window and there's a hint of a sun that's coming up. It's looking like it might be a sunny day here. So we would write down sunny and we would start to collect data in kindergarten and collect that and chunk it together and put it together and make some meaning out of that. That's part of computer science and it's developing the skills. And so when we say a computer science context, we're saying situate mathematical ideas like that first math benchmark in everyday real world computer science situations. So when we think about the rigor stool, you need to be spending approximately a third of your time on real world applications. And a lot of times that can be computer science. And you're probably already doing it. You just maybe not thinking about it explicitly so that you can highlight some of the language that you're doing. Let's look at one more example for 7th grade. In 7th grade, I was like, let me step it up. Let me go to applying the mathematics. And I looked at this 7th grade benchmark and it uses the phrase hierarchy of operations. You might be like, what's a hierarchy of operations? Some of you maybe have called that order of operations, but a more attending to precision term would be hierarchy of operations. And I looked and said, when we look at the computer science benchmark for this, both math and computer science require following a structured set of rules and a process to process expressions and operations correctly. And so the practice that I thought I could engage in is algorithms, repeatable processes that arrive at expected results. And then it's said to connect the order of operations in math to a sequence of steps in an algorithm. So I want students to collaborate and persevere. And I thought about what I did when I was in a 7th grade classroom. When I was teaching 7th grade, I was working at a K-8. And this was the picture that was in the bathrooms because the kindergartners needed an algorithm for knowing how to go to the bathroom in the right order. I didn't realize when I went there, because it made me laugh, that's why I took a picture of it, that they needed help in understanding the algorithm and the steps of going to the bathroom. But in math, we have algorithms that we engage in. These, by the way, are really common math expressions in 7th grade that students get wrong because they're all using different algorithms to do these problems. This is how I talked about order of operations in my own 7th grade classroom. There's not one right way. I know a lot of you might be thinking, oh, please excuse my dear Aunt Sally, and things like that. All of those things come with things that students get wrong all the time and have misconceptions about. And my thought is about computers need you. I was talking to my cousin yesterday who works in computers, and he was like, but if you tell the computer the right thing, it will do the right thing. And so, you know, we were talking about that. And so I use this thing from Survivor. I've linked to it if you're interested. I blogged about it when I was a 7th grade teacher. And I use this Survivor propeller heads challenge where the people in the challenge had to like run through an obstacle course and find all these operations. and they had to memorize them. And then they had to bring them down after they memorized the operations and write them down. And you can see this contestant's JT even wrote down PEMDAS, and they had to solve the expression. And it turned out I hated this challenge because the winning answer did not follow the order of operations. It did not follow a computational hierarchy. It actually was just done left to right, and the person that won had to solve it left to right. And so I love using it in my classroom. And then I challenged partners in my classroom to say, hey, can you work together to get what should have been the right answer on Survivor to this thing? And so I have them collaborating together. They take turns doing a step, but they also has to persevere because, like, dude, look at this. You're going to get rational numbers, and it's a lot of steps to get to where you're going. But in those discussions, they have to keep evaluating and applying a set of specific things to think about. What would I do? All of these are connected to that computer science benchmark using flowcharts or pseudocode to address complex problems. And if you look at this, you could have your students not just think about the traditional, please excuse my day around Sally, but writing it as pseudocode. Number one, get the mathematical expression. Two, find and calculate parts. Or I think even better yet, in addition to pseudocode, I think students would understand whatever you use as a hierarchy and ask them to take it and turn it into a flowchart. Understanding how to create flowcharts is going to build computer science skills. So how do students learn math? We give them experiences first. And in this case, I'm arguing that some of their experiences should be things that build computer science skills. So Sarah's going to give you one or two quick things, and I'm going to tell you where to find all this stuff, and then we'll be done for the morning.
So, as Sara was describing, a lot of those same steps are the steps that we would do in computer science to solve a problem or to create something. This is not a step-by-step process like the good old scientific method that we don't use in science anymore, but it is a way that all of these different computational thinking practices connect with each other.
To Geo, just tell your team and listen.
And so where can you find all this? Well, for all of the context, I did this for a real world. I put together a toolkit for you. And in the toolkit, you will find all those definitions that we talked to. You will find some planning documents for planning for computer science. And then you will find grade level sheets that link the grade level benchmark to the computer science benchmark that it goes with. And so if you want to start planning, you can go and find that. If you want to find the stuff that Mark and Jillian and Indriani put together, I've linked it on the task analysis guide up at the top where you can unpack each of those things. All that stuff is linked in the toolkit. Where can you find the toolkit? You can go to the link that's been in the chat and you can find it, or you can find it on this document, because everything in this whole webinar series is linked there. If you're watching the recording, you'll find it down below. Our next webinar is December 3rd. We'll be looking at financial literacy context. Get excited. That's what's up next in December. And I'm really glad you could be here. I want to give a big shout out and thank you to my colleague, Sara Carter. She is super knowledgeable and knows a lot of things. So Miigwech, we're super excited that you could join us today.